All right, sorry we're 3 minutes late getting started, but let's move from here. First, any questions on anything we've done so far? All right, we were in Chapter 2, First Order Differential Equations, 2.1, Solution Curves without a solution. Pretty interesting, huh? Solution curves without a solution. Almost sounds contradictory, doesn't it? So let's look at, on page 40, bottom half of the page, they're talking about solution curves. Now, this is where without a solution comes from. Without solving an autonomous differential equation, we can usually say a great deal about the solution curve, okay? So if we know it's in one of those regions and you have an excluded value, in fact, let me go to this kind of slide here. Trying to see if anything here really is what they're summarize what they're getting at, if I can figure out some way to say it a little bit better. All right. They're starting with this. What if you have some regions here? And let's say one region, that's not supposed to have a bump in it. There's your y of x is equal to some C2 up here. And y of x is equal to some C1 down here. Now these are autonomous equations. Remember, that means there's no x dependence, okay, on the differential equations. Your whole differential equation is a function of y and y alone. And for some reason, you have places where you have these critical values, that's what the C1 and C2 stand for, in y, so that indicates places where these are 0. The y's are 0 at C1, the y's are constant at C1 and C2. There is no, your slope of your differential equation, dy dx is equal to 0 at those two values, okay? Now, and you know that x0, y0 is a solution, okay? Trying to find where they say that, but yeah, here we go. Okay. So if through any point x0, y0, and r, there passes only one solution curve, okay? For the sake of discussion, let's suppose that there are two critical points, C1 and C2, C1 being less than C2. The graphs of the equilibrium solution, y is equal to C1 and y is equal to C2, are horizontal lines. And these lines partition the region into three subregions. Here is R1 up here, R2 down here, and R3 down here. Okay? Now, you have some value x0, y0 is a solution. And there's going to be only one curve that goes through that solution. Okay? Now, if that's in one of these regions, then it has to stay in the region, okay? And I drew it in R2 here, so they kind of leave it hanging here, which doesn't sort of make any sense. But you know it's got to curve and go like this, and then probably curve and do like that, okay? Now that could or may not be the solution curve, but it goes through that, and if that does fit everything else, that could be a solution curve. Now, I'm trying to see where the what they're saying is your function, if that represents some function, alpha of x, is either going to be monotonically decreasing or monotonically increasing. It can't change direction in there because you have that y represents the slope. The slope is 0 up there, 0 down here. For it to change direction, you have to have another 0 somewhere in between. So in between, in that region, R2, it's got to be monotonic. It has to be either strictly increasing or strictly decreasing. I drew it decreasing in this example. Okay? All right. I think that's all they're saying here. Now the last bullet they have on the top of 41, top of the page, if y of x is bounded above by a critical point C1, and so y of x is always less than that for all x's in that graph, then it must approach the equilibrium solution there as x either going to positive or negative infinity. I think if y is bounded, that is above or below by 2 consecutive critical points, then the graph of y must approach the graphs of one in one direction, one in the other. Seems pretty obvious. I don't know. Here's another. Now, they're going to flip things around on us here. So let me change this graph, wipe out this one. Okay, and draw in what they're suggesting. Oh, this is example 3. Sorry. Example 3 revisited. Okay. This first critical point here, the top one, is, okay. Let me erase it all. Start over. Okay. If you go back to example 3, where dp dt is equal to p times a minus bp. Okay? So p equals 0 is a critical value, and p is equal to a over b is the second critical value. So let's just plot that one in somewhere here. Let's just say right here. This is the p-axis, this is the time axis, t-axis. And this is p is equal to a over b. All right. And this is p is equal to 0. Okay. So we call this R3, R2, and R1. All right. Now, the 3 intervals determined by p are the phase line. And remember, the phase line was just the vertical axis here. It showed our critical point here, and it also gave the directions, okay? In R1, negative infinity is less than P is less than 0, so you know you're somewhere in there. R2, 0 is less than negative P is less than A over B, you know you're in there, and R3, so that's pretty obvious, it's greater than P, less than infinity. T is going anywhere from minus infinity to positive infinity. The phase portrait that we saw before, 2.1 well no, this is 7, is decreasing in R1, and that's what they told us it was. So they show some P0 here. Now, why they use the same symbol, I don't know. P0 here, okay? Now, this doesn't have to be approaching anything. This can be going to infinity, but it has to cross here, and because it doesn't have to wiggle like that, because it's approaching P equal A over B, it's got to have that as an asymptote, okay? So that can be one potential curve. Now, in the middle part, we had that it's an increasing function. So if it's an increasing function and it goes through a P0 here, and again, they use the same symbol for it, then it has to be coming from here, going here, and then approaching that as a horizontal asymptote. Now, what we don't know is how tight this curve is. It could be a real gradual one like this. It could stay here and then jump up and be very sudden. It could be doing anything like that, okay? But it has to be approaching 0 here, slope 0 there, slope 0 there, and it has to go through that point. So it has to be increasing everywhere in the region between those two critical points, 0 and A over B. And then for some reason, no, it's decreasing at the bottom part, so that means it has a horizontal asymptote here, and if it's going through this P0 here, then it could be doing anything down here. Going to negative infinity, it doesn't matter. Okay? Now, and they talk about this ad nauseum, and I can't see what the issue is. If you know your critical values, that's where your slopes are 0, okay? And that's, it's autonomous differential equation, so there is no y dependence. They're all, no x dependence. They're all on y. In this case, it's p. No time dependence. So your curves have to be monotonic in the regions. They have to pass through the indicated points in the given direction. So how you draw them in, that you would need some other value or something, but you would still have to, this could be coming in gradually here. It could be coming in very sharply here, but it has to be decreasing here, increasing here, decreasing there. Because that's how they gave you the problem. Now, did he come in and get a marker from here?
No, testing on the board.
Okay. Yeah, I was going to say that's his mark. I can tell. And it wasn't there before because I would have noticed it. I just happened to notice it now. I left that up because the morning class had it there. And I thought it might be important for them to have. I had to erase this board because that's the one I projected on. Okay. That ends, example 4 ends at that little square near the bottom of page 41. And let's see what the next, they do some talking here, but they don't have any illustration of it. So let me see if there's anything I can fill in the talking here. In a subregion like R1 that I just had here that I took off, that bottom subregion here, where P is decreasing and unbounded below, we must necessarily have that P of T is approaching negative infinity. Do not interpret that last statement to mean that P of T is approaching negative infinity as T approaches infinity. We could have P of T approaching negative infinity as T is approaching some value T, capital T, where T is greater than 0, as a finite number that depends on the initial conditions It's just saying it could have a vertical asymptote. I don't know. There's too many suppositions there. I can't really follow what their point is, okay? Except it could have a vertical asymptote, and that sort of makes sense. Here's a differential equation. Now, they don't do anything, but this is back in example 2. So if you turn back a page, dy dx is equal to sine y, okay? And we had several graphs of that. No, they didn't show any graphs of that. Let's see what they're saying. S autonomous has an infinite number of critical points since, okay, so let's do what we've been doing before on this one. dy dx is equal to sine y. Okay. It has an infinite number of critical points because n pi is a critical point. So obviously your x-axis is a critical point because your slope there is always 0. And then pi halves its 1 at pi, so that would be just past 3. There's a critical point, and just past 6, a little further past 6, 6.28. There's a critical point. At negative pi, you have a critical point, 3.14, negative 3.14, and negative 6.28. I can't draw very well. Okay. Infinite number of critical points, you keep going up and down, and it just keeps going. Okay. Moreover, we know that because the solution passes through the point 0, negative 3 halves. Now, did they tell us that in the problem? Yeah, they told us that in the problem, that y of 0 is equal to negative 3 halves. No. Y of 0 is negative 3 halves. So negative 3 halves is right there. Okay? Now, there's nothing here that tells you which way it's going. It's bounded above and below by critical points, below by the minus pi. This is minus pi here. This is minus 2 pi here. This is 0 here, pi here, and 2 pi here. And then infinite, keep going in both directions. Okay? Now, if you pick a value, okay, y is equal to, say, pi halves. Here we know it has to be increasing because it has a slope of 1. dy dx is equal to that when y is equal to 3 halves, well, pi halves, then you have a slope of 1. So that means this curve has to be doing something like this. And when it's down here, it has a negative slope. Sine of negative pi halves is minus 1. So this will have a slope down here well, negative 3/2 is going to be like this, so this has to be like this. And then this one would be like this, and this one would be like, whoops. Okay, I didn't draw, well, it comes in late, but it does. Now, I put them like that, they put them slightly, well, no, I'm sorry, I'm on the wrong page here. But anyway, that's one representation of what this could look like. Could be sharper, steeper, less steep, whatever. The slope should be 1 right here at, that should be a 1, so I probably don't have that one steep enough. That one doesn't look too bad. This one probably isn't quite steep enough, and this one I think is off by a bit. But anyway, you do what you can. You may not know the entire solution, but you know enough to approximate it. Let's see if we can do this with example 5. Completely different problem, so let's go to this. Here's a differential equation. dy dx is equal to y minus 1 squared. Okay? Does that have any critical points? At y is equal to 1. Okay? Let's do, this is 1, 2, minus 1, minus 2, just to use our graph a little bit better. So here's a critical point right here. Horizontal slope all along there. Okay? Now this is a double critical point too. Okay? And the other thing you can tell here, this derivative is always increasing. Second? Always positive, increasing. Okay, the derivative. So that means wherever you go, it has to be increasing. Now, for an initial condition, y of 0 is equal to y0, and that being something less than 1, what's that? Well, their graphs aren't matching up what they're saying here. We conclude that a solution y of x is an increasing function from negative infinity to y is less than 1. That would be anywhere over here. It's an increasing function. And it's also increasing on the other side too. Now, what they haven't figured out yet they just make those statements. Okay. Here they give you something else. Y of x is equal to 1 minus 1 over x plus c. They say that is a one-parameter family of solutions of this differential equation. I'm trying to see if that makes sense. let's take a derivative of this. Y prime is equal to minus 1 over x. Okay. Let me rewrite. Okay. Y of x is equal to 1 minus x plus c to the minus 1. So y prime of x is equal to 1 over x plus c squared. Okay. And y minus 1 would be minus 1 over x plus c, and square that, and you get 1 over x plus 1 squared, or x plus c squared, and that's exactly what you got here. So these two are indeed true. That is a solution for it. Okay? Now, from that, notice your differential equation depends only on y, but y depends on x. Okay? And from our solution here, we know that x can equal what? Say again? X cannot equal what? Minus c, exactly. X cannot equal negative c. Now, they didn't say whether c is positive or negative. Let's just assume that it's positive, so negative c is going to be negative. Oh, here they go a step further. A given initial condition determines a value for c. For the initial condition, say, y of 0 is equal to minus 1. Okay. All right, what does that tell us? Let's plug that in here. When x equals 0, you get minus 1 is equal to 1 minus 1 over c, when x is equal to 0, right? Minus 1 on this side, 1 minus x over c on that side. Or 1 minus 1 over c on that side, because x is 0. Okay, so let's subtract 1 from both sides, and you get minus 2 is equal to minus 1 over c. Multiply both sides by minus, and you get c is equal to 1/2. Okay, so c equal 1/2. Let's plug that in here then. 1 minus 1 over x plus 1/2. All right. Now that tells us if we, this time I'm only going to do minus 1, minus 2, minus 3, 1, 2, 3. Okay. All right. So x equal minus 1/2 would be right here. This is going to be a vertical asymptote. You cannot ever touch or cross that. Okay? Now, they also told us when y is equal to 0, x equals 0, y is equal to minus 1, Here's x equals 0. Here y is equal to -1, right down here. Okay, that fixes where you are here, because you know that this slope is always positive, so that means you're going up here to a horizontal asymptote here, approaching a vertical asymptote there. That's fixed. That's done. No choice around it. It's positive slope, that point, horizontal, vertical asymptotes, you're stuck. Now, what that probably means is up here, you're up in this quadrant. Now, you have no zeros there. You're just going to need to plug in some values and see. I would do x equal -1 and see where you are. X equal -1, this would be -1/2, right? The denominator. 1 over a -1/2 is a -2, and 1 minus a -2 is 1 plus 2 is 3. So I'm off scale. Okay, but somewhere up here we've got our value. So that means it's doing something like this. I can't draw it completely because I can't get to that point, but that's what the function is doing. Again, it has to have a positive slope everywhere, has to approach a horizontal asymptote, vertical asymptote, and because the point -1, +3 is on it, you have to be going that way. Now, that's the first part of example 5. The second part says this. Now, y is equal to 1 over, okay, sorry, I've already done that part. All right. What if our initial condition, I think I'll change colors. You pick me a color, not black. Blue, light or dark? Dark. Okay, let's pick that one. Now let's do same equation. dy dx is equal to y minus 1 squared. Same horizontal asymptote here because that's the same critical value. Okay? But this time we're going to have initial condition y of 0 is equal to 2. So when x equals 0, y is equal to 2. So that puts us up here. Okay? Now, okay. We're changing the entire problem around now. Says a given initial condition in this case, y and I don't think they give us enough information to do it. They just say, this is what you got. They don't say this is how you get it. They just say this is what you got. Let me make sure of that. let's say we have our same initial condition here that are the same function value here. Y of x is equal to 1 minus x plus c to the minus 1. Probably don't want it in that form. The other form would have been better. Let me write it in that form. Okay. 1 minus 1 over x plus c. Okay. Okay, plug in y of 0, and y of 0 here is 2, is equal to 1 minus 1 over c, sorry. 1 over c, because x is equal to 0. Same thing we did before, okay? But now we get 1 is equal to minus 1 over c, meaning that c is equal to minus 1, right? That's a whole new ball game here, because what your solution is now is y of x is equal to 1 minus 1 over x minus 1, right or not? Okay. Now in this case, your vertical asymptote is now x equal 1. So here's your vertical asymptote now. Same horizontal asymptote, y equal 1. That didn't change. But now this line is over here. We have this as our initial condition, that point, so this has to be going up here and down here. Okay? That seems to indicate, and I think it does, that the other part's got to be down here somewhere. But I don't think there's enough information to tell us that. Let's see. Well, yes, it may be, because we know that when y is equal to 0, you know, somewhere here, and we didn't do this before, but let's try it. We get 1 is equal to 1 over x minus 1. Okay, so x minus 1 is equal to 1. So x minus 1 is equal to 1. X is equal to 2. So there's a point there too. And once you have that point, you know it has to be going like that. And that's, yeah, that's exactly what they got to. So I'm not absolutely certain what they're trying to show with this, except if you have a different initial condition, it will change your asymptotes as well as changing your function values. And of course, it's got to. So, and so you can get your solution curves, but never know a solution, I guess is what they're trying to say. But no, this one, you know it because you have enough information to get that. Now, the next issue they're going to talk about here are that of attractors and repellers. They're spending a lot of time on these autonomous differential equations, and yet they do very little with them, okay, later on. But I guess they got to do something with them now just to get them out of the way. Okay, Suppose that y of x is a non-constant solution of an autonomous differential equation, and c is the critical one of that differential equation. There are basically three types of behaviors that y can exhibit near c. Okay. And let me clear all this out of the way. I don't think we need this anymore. I was hoping we would be able to see something using these, but I don't think so. Watch me regret that, but let's do it. Okay. Three basic types of behavior that y can exhibit near c. So let's say our c is here. We go back to black. Let's say the c is right there. Y is equal to c is right there. Okay. Now, it can be, and that's a critical point, so you know you got a horizontal asymptote there. Okay? One thing is that y could be decreasing there, increasing there, and what they say here is this is an attractor, okay? Because this is got to be doing something like this, and this has got to be doing something like that. So you don't have a curve over here, but it's an attractor. It's pulling the values toward it, okay? Now, next condition is this one. Okay? The arrows are that way, meaning y has to be doing like this, and y has to be doing like that, because it's monotonic in both regions. Well, that they classify as a repeller. Okay. So that's condition 2. Condition 3, I should have left that one alone. It's going up here and up here. Then you have this kind of a motion like this. Okay? Now, that's neither attractor or repeller. That is the critical point is said to be unstable because it approaches it from one side but not from the other. Okay? And the last situation is this one. Everything gets turned on its head here, and it's repelling, it's going down in both circumstances here, so now it's going like this, okay, or however it's going. That would then be another situation where you would have an unstable situation, okay. So asymptotically stable, when both arrowheads on either side point towards C, that's asymptotically stable. And that's also said to be an attractor. When both arrowheads on either side of the dot product labeled C when both arrowheads on either side point away from the initial point, that's called a repeller, which we already said. And actually the other is when they both are pointing in the same direction. That's actually called semi-stable, okay? And again, these are just words And as far as I can recall, they never come back and use them again.
Seems kind of pointless.
What's that?
It seems pretty pointless.
Yeah, it really does. I'm trying to find some value in it, except for, you know, when you're actually solving these things. If you are coming to the asymptote from both directions, then it doesn't matter where your initial condition is, you're always going to be going to you're going to the same value, whether it's up here or down there. So that then seems to be stable, and that would be when it's an attractor. When it's going the other way, and they're coming from the same but going opposite, then obviously that's an unstable situation. Neither one of them are going to work. And when you go from one direction, let's see how that, like this, you know, they're going, or like this, they're both going down. I can see semi-stable because you always have one direction that it's okay, but not the other. So unstable would be like this, or not coming at all. So, but yeah, but what the thing is, they don't tell you anything to do with that. Okay, what's that?
Like a real world.
Exactly. No real world application. I'm sure there must be some, but I just don't know what they are, and they don't present any here.
You're keeping a C value with.
Yeah.
I don't know, something for a plane or something. You want to,
Yeah. And this next thing, autonomous differential equations of direction fields, it's what we've been using all along, and we saw that at certain values they always are pointing the same way because they're only dependent on y. So all along that y, it's going to point in the same direction. So I don't know for certain why they're trying to make a big deal about that value, but anyway, we'll move on from there. The translation property, it's a lot like what we had way back in pre-calculus algebra. If you have something that looks like this, y of x is equal to some function of x minus k, okay, whereas k is a constant. If you had some other function, y of x is equal to f of x, then this would be a horizontal shift to the right. So if this thing were doing like this, it would now go like this. It's shifted to the right k units. From here to there would be your horizontal shift of k units. Okay? And let's do the same type thing. They're going to give us a little bit more of an example here. dy dx is equal to y times 3 minus y. What can you tell me about that? Just looking at that, what can you tell me? What do we, yeah.
Y is equal to 3 over y, something like that.
Okay. Well, what do we usually want to know when we have something about, when we're dealing with slopes? First derivatives, where it's equal to
0.
is a critical value. What's your critical values here?
3.
Y is equal to 0, and y is equal to 3. Okay. So you've got that, you can write down immediately. Okay. Now, That splits it into your typical three regions. They usually list this as region 1, region 2, and region 3. Okay? Now, seems like all they're getting at is this thing at the bottom here. If y of x is a solution of an autonomous differential equation, autonomous dE dy dx is equal to some f of y. It makes it autonomous. There's no x dependence on the right-hand side. Like that one up there. Okay? Then y1 of x equal y of x minus k is a constant. This is also a solution. Okay? That's just what they're claiming. It is also a solution. Okay. Now, with that in mind, let's go to what they claim here. Okay. I'm going to write them down. They seem like they're all disjointed, but okay, let's do the example. Y of x is equal to e to the x. Okay, that's good everywhere. Okay, and they say that's the solution for the initial value problem. Dy dx is equal to y. Okay, that certainly works because derivative of e to the x is e to the x, so derivative is equal to that. So that certainly does work. Okay, and also that y of 0 is equal to 1. That works for e to the x too. When x equals 0, y is equal to 1. Okay. And they say that so is this. Dy dx is equal to y okay. Same thing we said before. This time they're going to say y of 5 is equal to 1. Okay. So what they're saying is the solution for this one would be similar to this solution except that you shift it to the right 5 units to get the same value, which is just what we've done for. So y1 of x is equal to y of x minus 5, where you shift it there. So this is equal to e to the x minus 5. Now, I don't see why go through all that. That's just a shift of this. Y of 5 is equal to 1. This is still true, but now you shift it that y of 5 is equal to 1 rather than y of 0. That means 1, 2, 3, 4, 5. There's your point where it's beginning, and your exponential function is now going to go like that. So it's just a shift to the right 5 units. Okay. I don't know what's supposed to be so incredibly remarkable about this. That's just what a horizontal translation is. And let's just leave it there. Thank goodness they didn't have any additional remarks here. Homework exercises here, direction fields, which we already had finished, 1 and 3, if those answers are in the back. Any of the odds 5 through 11, if those answers are in the back. 13, if its answer is in the back. 15, if that answer is in the back. That's all, folks, for 2.1.1. 2.1.2, number 19, if that answer is in the back. Any of the odds 21 to 27, if those are in the back. 29, if it's in the back. And that's it for those. Now, they talk about some mathematical models here, going back to some of the things we did. In 1.3, you can look at those if you want to. I don't know if those answers are in the back. If they are, you can look into them. Now, finally, 2.2, we're going to get to something that I wish they would have started the course somewhere right around here, okay? Because I don't know, I'm sure there's some good was in the rest of it, but this is when we finally start solving differential equations, not just saying, this is a solution, verify it. This is a solution, or we know if this is true, that's true. Now we actually start solving. We start with separable, okay? So this is the easiest kind. We'll begin our study of solution methods with the simplest of all differential equations, first order equations with variables that are separable, okay? Because the method discussed in this section and many other methods for solving differential equations involve integration, you're urged to refresh your memory on important formulas such as blah, 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 okay? Integration by parts, this kind of stuff. So let's consider a first order differential equation. Let me go to this page. dy dx is equal to g of x. Now this is different from what we were just doing. Before we had g of f of y, okay? No longer that. We just have x dependence on one side and derivative on the other side. Not y dependence on one side and derivative with respect to x on the other side. This one, far easier to deal with, okay? What we do here is what you've seen me do, I think, several times. Let's write this in differential form. What would that be? G of, that's an x. It's an ugly x, okay. G of x dx. And if you do that, you get y's on one side, x's on the other side, integrate, integrate. And this will give you y. You don't need 1 plus c, so wait and do that on the other side. And this would be whatever the antiderivative of g would be, let's just call it capital G of x plus c. There you solve it. If you know the antiderivative of g of x, that's what it is, okay? Now, there weren't any variables to separate. They were already separated. Once you wrote it in differential forms, You got y's on one side, x's on the other. Piece of cake to do. If only they were all that simple, okay? So let's do one that's actually an example here. Well, it's not called an example, but they say for example. dy dx is equal to 1 plus e to the 2x. So what would you do? Yeah, write it in differential form. Take the dx from this side, put it on that side. In a sense, you're separating those two variables. Now you got all y's on the one side, all x's on the other. Integrate both sides. That's integrate both sides. Decided to put parentheses around it and messed up my integral sign. Okay. And what does the left-hand side give us? Y. Why not? Right-hand side? X plus e to the 2x over 2, right? You got the thing. One other little thing, plus c. Got to have a plus c. Now, if in doubt, not certain of that answer, take a derivative and see if you come back to getting this. So dy dx would be 1 plus 1/2 e to the 2x times 2. The 2's go out. 1 plus e. Yep, you got it. And derivative of that equals 0. So yes, that checks. If only they could all be that nice. Yeah. Now, that is if the right-hand side is only a function of x. Okay? If it's not, if it's a function of x and y, so dy dx is some function of both x and y. Okay? Everything depends on what you can do with that f of xy. Okay? If the f of xy can be written this way, g of x times h of y. If you can separate one function, rather than having one function of two variables, split it into a function of one variable times a function of the other value. Notice this is not plus, this is times. This is not minus, it's times. Now if that were division, it's still okay, because that's one times 1 over the other. So multiplication or division of the two would be okay. Just adding and subtracting, no, you can't do it. But if they're multiplied or divided, you can go. So a first order differential equation of this form and that is dy dx is equal to g of x times h of y, is said to be separable or to have separate variables. Okay? So let's look at some examples. All right, to erase? Here's one. dy dx is equal to y squared x e to the 3x plus 4y. Wait a minute now. I see a plus sign in there. Is that separable or not? It's what? Okay. Exactly. You could write this as y squared x e to the 3x times e to the 4y, right? Because anytime you raise any entity to a power, as long as you keep the same base, have different powers, but the powers are added, you can split that into the product of their bases, raised to that. It's a rule of exponents, okay? E to the 3x times e to the 4y, same base, keep the base, add the exponents. So you're just doing that in reverse, and now you can write that as y squared e to the 4y, there's your g of y if you want to call it that, times x e to the 3x. And there's your f of x if you are stuck on naming them that way. Okay? Now, does this mean that's going to be easy to do? Easy to separate maybe, or somewhat easy to separate, but then getting the functions, you still may have some work to do. But really, it's not too bad. That's going to be, on both cases, I think, integration by parts. Looks like the way to go on both of those. Okay, now they're not saying to solve them yet, but what about this one? dy dx equal y plus sine x. Separable or not? No way. No way I can think of at all to separate those two. Okay? No way to make that a product of some function of x times some function of y. Not going to happen. Okay. All right. Now, once you get them separated, like we were talking about, dy dx is equal to some g of x, h of y. What do we do with them now? How do we actually separate them? We say they're separable because they're multiplied, but how do we actually separate them? Remember, you want your y's on one side, x's on the other. So obviously, the dx is going to go over here, right? Lose it here. What do you need? How do you get that? Divide by h of y. Okay? Now these go out, and now you have a dy over h of y is equal to gx, g of x dx. Now, it's easy to put integration signs on both sides, say, now integrate. This may not be a particularly easy thing to integrate, but if it is integrable, you got it. This may not be all that easy to integrate, depending on what the g of x is. But if it is, then you integrate. Okay? Remember, we had trig identities, we had trig substitutions, we had logs, we have lots of different tools to use. And in fact, that could be something that maybe you could do by integration by parts, maybe something by partial fractions. There's lots of exhaust all your possibilities. See if there's any way to integrate.
So it's just two integrals right there.
Yeah. Okay. Right. But some of them may be tough to do.
Like one's 1 over like h to the y dy, and the other.
Yeah. But this h of y could be anything with y's in it, and that may not be a particular like 1 plus sine y. That sounds pretty simple, but how are you going to integrate that? So you may still have problems on your hand, but do it. You got integration tables, look them up, whatever. Okay. Now, how are we doing? Almost through. Let's hit one more. we're going to see this form a lot, okay? P of y times dy dx is equal to some g of x, okay? In fact, there will be times when we want them in that kind of a form. But if that's all you had, that is definitely separable, right? How? Okay. Or write it in differential form, which is exactly that. And then you integrate both sides. As long as this is an integrable function and that's an integrable function, you've got it knocked right there. Now they go through all sorts of things here, and this is one of the favorite techniques of this book. Now let's call this my 1 over h over y that we had before, let's call it p of y, and then let's call y some phi of x, and they just keep introducing new substitutions in here, and they have a string of things out here that after a while you say, what is the point here? And it part of what they're saying here is if you can get it into something that's integrable, and maybe use integration by parts or something else, but if you can integrate it, then just go on and integrate it, okay? And they wind up then at the same point getting to this thing that I've got right here, and then it's just saying, call this one h of y and one g of x, and go for that. So there's one thing they do say, when you're integrating this, there's no reason to have a plus c here and then another plus c1 here. Just wait and put all the c's on one side or the other. It doesn't matter which, because whatever they are, you can add or subtract to the other side and it's still a constant. So you only need one constant of integration. You don't come up with a two-parameter system for that, because this is a linear, is a first-order differential equation. So you only have one constant, okay? And I think we're out of time. So we'll start with example 1, which is a really nice example. I wish we'd have had time for it just so we could have gotten one done today, but we didn't. So I forgot to bring my pencil, my eraser up, so use the sorry eraser again. We didn't do any examples, so no new problems in this part, but starting from tomorrow, Wednesday, we will be doing solving differential equations. And then we'll move to linear equations, solving linear equations, initial value problems, solving them. And then we'll get to some that you may not be able to solve, but at least you'll recognize them. So anyway, for the rest of this chapter, we will be actually doing techniques to solve them, not talking about what the solution without solutions may look like or not look like, or something, which to me got really bizarre. But we're making progress now. Actually, they'll go too fast because they're fun to do. Okay? And then we'll get into other things later. But we'll be a while actually solving differential equations.